Hello, everyone. I'm gonna just wrap up here, the last part of section 5 and talk about an important property that comes up in the statistical literature and beyond, and that is the behavior of maximum likelihood estimators. And so it turns out that maximum likelihood estimators here will always converge to something. And one of the things that we would like is for the maximum likelihood estimator to converge to the parameter it's estimating. So I'm going to take a simple case. I'm going to basically prove to you that it's true. I think I would be less worried about the mechanics of the proof, although the mechanics are things you have already seen. It's going to be sums and averages of a likelihood ratio, and things are going to go to infinity or zero, and certain probabilities are going to go to 0 or 1, and then that's going to be it. So it's mechanics that you've seen and you can understand. And I think it's helpful to get a sense that these things can be proven in general for models that are straightforward. So suppose I have a finite parameter space. So my parameters here are all my particular parameters. There's k of them, or k plus 1 of them. I'm going to take this as a simple case. This would be like having trying to estimate a mean in a normal distribution, and then the mean could only be one of 100 particular values, for example. This easily generalizes to more complex parameter spaces, but the proof needs more complex mathematics to do it. And I think this particular case is one that's very accessible, and we don't need any more tools than we already have. We already know enough to prove this, and it's a pretty cool idea. So let's suppose we collect data. So we collect some data from a model. And the data are independent and identically distributed. They all come from the same model. And so, for example, that model, F might be normal mu sigma squared, for example. And in this particular case, let's assume we know sigma squared. So maybe it's normal mu 1. And I want to estimate the mean mu. And in fact, we're using theta, so you can imagine it as being normal theta 1. Okay, so let's just put that here as an example, normal theta 1. This could also be binomial 10 theta, where theta is the probability of success. This could be lots of different things. And there is some true value of the parameter, theta naught. That's the actual true value. So that means the data, and what this means is we think of the data as coming from f of x theta naught. That's what's generating the data. Okay. And from this model, actually, I'm sorry. It's not actually that model. So let's get rid of it. We don't know this. We want to learn what is the true theta. So we actually end up using this model. We use a f of x theta. And from this model, we get the maximum likelihood estimator, theta hat. That's the MLE. And I want to know, as my sample size gets bigger, does that thing converge to theta as the sample size gets bigger? Well, let's take a look at what we know. So I'm going to calculate the probability that the maximum likelihood estimator is not the truth. Don't forget, now here's my parameter space, and I can count up all these different options. So I want to know, what's the probability that my maximum likelihood estimator is not theta naught? If it's not theta naught, it could be theta 1, it could be theta 2, it could be theta k. And each time you collect data, that maximum likelihood estimator is going to be a different value in here. But as n gets bigger, it's going to get pushed closer and closer and closer to theta naught. So I'm going to compute the probability that I have a model, okay, and that has a value of theta that ends up being bigger than theta naught. well, no, so wait a second. What's going on with this? Why is, let's take a look at this. Why would this be intuitive? Well, the maximum likelihood estimator is the theta that maximizes the likelihood, right? And here is the likelihood. So this is a case where there's at least one value that has higher likelihood than the truth. That's why this f of theta j is bigger than f of theta naught. And I can rewrite this as a likelihood ratio. So what's the probability that the likelihood ratio is bigger than 1 when it supports some false value over the truth? And I want to know, how often does that happen under the truth when the data are being generated from theta 0? And the key thing is that these two things are aligned. Of course, we've seen this already, right? But this is what it means to observe a maximum likelihood estimator that's not the truth. Your likelihood ratio for the false value is bigger than the true value. And this will happen in small sample sizes, no doubt. But as the data gets large, what would you like to see? Well, as the data gets large, like you may start out, with a likelihood function that looks like this. That might be your likelihood function. Here's theta. And let's say the truth is here, theta naught. Okay, actually, let's go back and then let's make this, change the color. That's the truth. What we hope happens is that over time, for example, well, then I collect more observations and maybe I get a likelihood that looks like this. Well, that's shifted the wrong way. So then maybe I collect more observations and I get a likelihood that looks like this. Well, now that's centered over the right place, right? Here is the MLE. Here is the MLE is here, in the red case, the MLE is here, right? And so what I would like to see is that this thing gets concentrated around the truth, and it does. You should do this. You should generate data from a distribution. You should draw the likelihood function. Just take the normal distribution or the binomial distribution and do this for yourself. And what you'll see is that eventually, like these likelihoods end up very tightly concentrated. I'm drawing blue here. It's a little bit hard to see, right around the truth. And that happens because likelihood ratios, I'm back to here now, likelihood ratios for the false value over the true value, which is what this is, being greater than 1, happen seldom. Well, how do we do that? Well, we've actually shown exactly this thing before. So let's take a look and let's do it. Well, here's the likelihood ratio. And I'm just writing it out as its actual expression, right? This is over all the data. And then I'm exponentiating the log of this thing. This is the same trick. And I'm multiplying by 1 here so that I end up with, this is the average that we want to see. Well, and so here, the average log likelihood ratio converges to the population log likelihood ratio. And I can remove this log. I can pop the log out of here, right? Out of here. This is Jensen's inequality. And then I know that this thing is equal to 1. So the log of 1 is equal to 0. And that's how I get that 0. So this piece up top here, and we've done this in class, this thing is going to go to some number that's a negative constant. If C is greater than 0, that's going to go to a negative number. Well, okay, so then if I go back to the original scale, this whole thing is going to converge to, this is going to be, so this is all going to be, this is C here, right? And here I have C less than 0, so I'm sorry. So let me change, let me edit this here, blah, 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 blah. That converges to C and C less than 0. Wow, what is that? C less than 0. And so this converges to the limit of E to the minus infinity, which is 0, right? Well, if the likelihood ratio is going to 0, what is the probability that the likelihood ratio is bigger than 1? this thing also has to go to 0, right? Because the likelihood ratio is going to 0. So it's always going to be less. It's always going to be less than 1. And that's basically it. That's the proof. So the probability that the likelihood ratio is bigger than 1 goes to 0, as we just talked about. And of course, now I'm going to take this and do. So the probability that you have a likelihood function at theta j that's bigger than a likelihood function at theta 0, the chance of that happening is effectively 0. Well, what does that mean? Well, okay, hold on, time out. Let's draw. There's my likelihood function. There's L of theta. Here's theta, right? And in fact, and let me put in another axis here. So this is really L of theta here. And then we can get rid of that. And here is, let's just say, here is the truth, right? So here's theta naught. And then, of course, this is the likelihood function theta hat. This is a case where, right here, this is L of theta hat. And of course, this is L of theta. So this is one of those cases where an L of theta j is actually bigger than L of theta hat. You know, this is some other theta j, right? And then this is, oh, I'm sorry, this is L of theta 0, not theta hat. Let me correct this. Going too fast. L of theta naught. And so what this property says is this is not going to happen in large samples. What does that mean? That means that the maximum has to be here. The max has to be at theta naught, which means you're going to eventually get likelihood functions that look like this. They're all going to be centered perfectly at the right place. So your estimate, your maximum likelihood estimator, theta hat, is going to have to go, is eventually going to end up at theta naught, because it doesn't end up at theta j, because theta j is never the maximum. Theta j is any other false value, no matter what it is. You can pick any one and substitute it in, right? And so the probability, so the one way to write this is the probability that the maximum likelihood estimator is equal to a false value, right? This is a false value, is equal to 0 or goes to 0. So the probability that the maximum likelihood estimator is equal to the truth is 1 minus the probability that it's equal to the false value, but all these false values go to 0. So the probability that the maximum likelihood estimator is equal to the truth will go to 1. There's a handout for section 5 that discusses this approach for the continuous case, which I don't think you need to worry about at all, again, unless you just want to look at seeing the notation. But again, I'm trying to get you sense. We're looking at the behavior of this function, of this likelihood function, which is basically our objective function at the moment. And we're understanding what sort of behaviors we have. And at least we have a nice property now. What we've shown is we've basically said, okay, look, you're going to start with the model f of x. Let me just use f of x given theta. I'm going to draw a bunch of samples from that distribution. And then I'm going to take some function of that data, right? And I don't know what to call it, but I'm going to get a maximum likelihood estimator from the data. And then what we've shown is that this maximum likelihood estimator will eventually go to the true theta. So if we started at theta naught, as the sample size increases. So we end up in the right place. And what we're going to do is, very interestingly, is we'll show what happens when the model's wrong too. So maximum likelihood estimators almost always converge to something. They don't converge to nothing. Remember, converging to nothing would mean that you sort of go off into space. Sometimes you're big, sometimes you're small. And in this case, we'll be converging to some point, and we'll have to see what that point is, if that point is the thing that we're the thing that we're interested in. All right. Thank you.